All right, for today, we're going to look at the derivative. And I think this is going to maybe take more than just one day. And then we're going to look at some graphs, kinematics graphs, and we're going to look at the behavior of the derivative based on these graphs. All right, so this is what we did yesterday, right? We answered a question where we found the average velocity in t2 seconds just by finding the change in the function over the change in time, right? So delta S over delta T, which works out to be the slope of the secant line connecting those 2 points, right? Today, where we wanted to go with this, where we kind of left off was with the question, how could you find the instantaneous velocity of the particle at T equals 2? Okay, and this is the picture we were trying to find the equation of that tangent line at T equals 2. And keep in mind, like we said yesterday, the tangent line is just the line that grazes the function. It intersects it at that one point of tangency is what we call it. Yes. Oh, I thought you had a question. Okay. So we have a point of tangency there. The function intersects it at that one point, and it shares the same slope as the function at that point. Meaning if I wanted this weird concept, but if I wanted to know what is the slope of the red curve at T equals 2, what I'm really asking is, what is the slope of the line tangent to the curve at that point? That's really what we mean, because how can you have a slope? It seems like that doesn't fit very well to talk about the slope of a function, right? A slope is a property of a line. Well, it's a property of a tangent to the function then. And if I were to zoom in, this is what we saw yesterday, if I just zoom in really far, you can see that as the curvature of the red function disappears, you can see that it begins to more and more closely be approximated by that tangent line. So they do indeed share the same slope. Okay? All right, so what is this file? I got to think what this one is. Oh, yeah. Okay, so any ideas? Any ideas how maybe I could go about trying to calculate what that slope of that tangent line is going to be? Yeah, what do you think? Do you need the secant line? Well, we don't. Yes and no. We don't need that secant line necessarily, right? Because that secant line is defining an average rate of change between 2 and 6. Okay. What would happen? What do you mean by that? Okay, what would happen? Oh, okay. Oh, yeah. Nice. Mudboard security. Need to bring in the big muscle, I guess, or something. I don't know. Yeah, so that's a good idea, right? What if we did something like this? What if we abandoned that secant line and instead, I did a lot of programming on this, can't remember which one's which. Yeah, something like that. What if instead we picked secant lines? Like if I were to draw that point in closer and closer and closer, look what's happening to the secant lines. The secant line, what did I just do there? Yikes. The secant line, finding the average rate of change between two points that are closer together, right, starts to look more and more like that tangent line we're chasing. Okay. And in fact, why don't we just draw this? Here's our tangent line right there. Why don't I just draw that point in more? Oh, I can't do that. I forgot. I got to do this, I think. Where's my H? Okay, that's what I'm using. Okay, that's right. So look, if I draw that point in more closely, look what it does. That secant line starts to look more and more like the tangent line. Everybody see that? Right? Look at that process. What do you mean? Well, yeah, so ignore what, that's just my programming stuff. You don't really need to know. Here, I'll just do this. You don't need to see all that stuff. What you just need to see is this. You just need to see that if I draw in delta x in this case, or I think this was delta t, whatever our input variable is, and as that gets smaller and smaller, the secant line starts to approach the tangent line, right? Starts to look more and more like the tangent line. This is the great breakthrough that allowed us to develop differential calculus. Leibniz and Newton came up with this idea, and it was the birth of differential calculus. Okay, they were pretty smart guys. So what could I do then? If I want to get the exact answer, notice that if I try to calculate the slope of the secant line, I can just go back to this one. If I try to calculate the slope of the secant line when I bring this point all the way back down to 0, oh, it disappears. How come? The same point, and if I try to calculate the slope of that secant line, then I'm getting 0 over 0. Rise over run is 0 over 0, which is undefined, right? So I can't actually, I mean, a secant is different than a tangent line, but what math vehicle do I have? What calculus vehicle do I have that we've been introduced to fairly recently that would allow me to figure out what that value of that tangent line actually is? What could I do? I'm trying to draw those 2 points closer and closer together. I can't actually make the difference between the x values, so call that delta x or delta t. I can't actually make it 0 because the function becomes undefined then. The slope becomes undefined. But what could I do? You got an idea. What are you thinking? How about that? What if we take a limit as delta x or delta t, whichever variable we're using, approaches what? 0. Yeah. If the bottom, if the run of that secant slope approaches 0, the value of that limit should give us the slope of the tangent line, right? So we should be able to use this vast knowledge of limits that we've accumulated to answer this question. And we can summarize that whole concept right there, right? If this is what we're defining as the slope of a secant line, right? It's f of x, we'll use x as our input now, f of x plus delta x minus f of x over delta x. That's just the slope formula, right? That's the slope of a secant line. Then the slope of a tangent line is just equal to the limit of the slope of the secant line as delta x goes to 0. Okay, so that's it right here. The limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. You guys might remember when you were doing all this practice with evaluating limits analytically, I actually gave you a problem that looked an awful lot like that. Remember, it had x's and delta x's in it. Why did I do it? Well, because you're going to be using those types of limits a lot now, right? You're going to be finding these slopes of tangent lines with this limit process. So this is such a big deal that we actually give this its own name. We call that the derivative. That is the definition of a derivative. A derivative corresponds to the slope of a tangent line at a specific value of x. So f prime of x, that's how we'd say that. That means the derivative of x is just equal to the slope of a tangent to the function f of x at that point x. Okay? So let's apply this. So there's our derivative function. We do simplify this a little bit. Instead of writing delta x, which is kind of clunky, a lot of times we'll just use h, so we don't have to write so much. We'll just replace the delta x with an h. So h is defined as the difference in the x values for the 2 points that we're using to define that secant line. Okay, and for notation, there's a bunch of different ways that we say derivative. This is probably, for our current exploration, of derivatives, this is probably the easiest way to think about it. It's just f prime of x. If the original function is f of x, then f prime of x means the derivative of that function, okay, which is our mechanism for calculating slopes of tangents to that curve. There's some other ways we do that. We also use the notation dy dx to represent a derivative. Why do we do that? Well, because it looks like a baby delta, right? The slope of a secant line is delta y over delta x, where delta x and delta y are some macroscopic quantities. Those are two distinct points, right, that are defining that secant line. Well, dy dx is just what you get if you shrink those macroscopic quantities in a limit down to where they approach zero, right? So they're like baby deltas. There's your dy dx. We could say y prime is a really abbreviated way of saying a derivative. Or you could use this notation, the derivative with respect to x of a function. Those all mean exactly the same thing. Why do we have so many ways of, and there's even more ways. Like in college, you might have a textbook that even uses other ways of writing the derivative. Why do we use so many? We do that in math. The context determines how we'd write the derivative. This way makes sense for us now when we get a little further along and we're dealing with non-functions or really difficult functions where x and y are tied together in the equation in a way where it's really difficult to solve for y. We're going to use a process called implicit differentiation to find these derivatives, and there we definitely want to use y primes. When we're doing our algebra, it makes it a lot more concise and readable than if we use these other more cumbersome forms of a derivative. If we're talking about slopes, oftentimes we use dy dx. If we're talking about a graph and slopes, but they all mean the same thing. So don't get confused by any shift in notation. On the assignment, I'll try to give you, problems that ask the question in different ways, but they're all asking the same thing, find the derivative. Okay, let's try one of these. So here's our goal. This is kind of a good goal. This is a pretty cool question we get to solve here now. Find the equation of the line tangent to this curve, f of x equals the square root of x at x equals 1. That's huge. You would have had no way to do this prior to today. This is the only way to do this problem. Okay. So what are the ingredients of a line? We want to come up with a tangent line. Every line has the same ingredients though. What are they? If I want to come up with the equation of the line, what do I need? Is it? Not Desmond. Well, okay. What do you mean by x and y? Like, what are the ingredients? What do you think? If I want to come up with the equation of a line, what do I have to feed into any of my different forms of a linear equation? A slope and a. But what do you mean though? I mean, I need a slope. If I want to define a line, I need to know the slope of that line. But knowing the slope of a line, that's not enough. I could have a slope of 1, but that line could be here, or it could be there, it could be there. The slope that's part of it. I need a slope. I need a point to anchor it to also, right? I need to know a point that this line goes through and the slope of the line, and those two things is enough, right? Those are enough. So the point is easy. If my function is f of x equals the square root of x, and I want to find the point of tangency at x equals 1, well, what are the coordinates of the point that our point of tangency is going to go, or that our tangent line is going to go through? In other words, what are the coordinates of the point of tangency? X is 1, what's y going to be? 1. How'd you get that? Plug it in. Yeah, right. So we know, good. So we know that f of 1 equals 1, right? Square root of 1 is 1. So we know we have the point of tangency then. Oops. When x is 1, y is 1. So there's half the battle. We've got a point. Now we need a slope. That's the part we couldn't do before. Okay, so if I want the slope of the tangent line at x equals 1, how am I going to say that? The slope of the tangent at x equals 1 is what in calculus? The derivative, right? That's going to be the derivative function at x equals 1, right? This is equal to f prime of 1. Okay, to find f prime of 1, though, let's first of all answer the question, what's f prime of x? Okay. So where do we always start? Well, we start with our derivative formula. What's the definition of a derivative? F prime of x is defined as what? How do we define the derivative function? The derivative of the function f of x is, it's just the same every time. It's just a formula. It's the limit of f of, let's go back. This, by the way, this part right here, I could have gone back to any one of these slides. Like if I go back to the original, to this guy right here even, this is what we call the difference quotient. Okay, the difference quotient is the slope of a secant line. So you'll hear that word a lot in calculus. Like this is, if I just circle all that stuff. Quotient means I'm just dividing two things, right? Difference quotient means I'm dividing the differences in the y values by the differences in the x values. So it's the difference quotient. That is the slope of a secant line, okay? So the derivative is just the limit of the difference quotient as delta x or h goes to 0, right? Okay, so then we need to start with the formula. It's the limit of the difference quotient, f of x plus h minus f of x. Think what that means. I'm gonna take the value of the function at x scooted to the right a little bit by h minus the value of the function just at x, right? That's how we're creating that secant line, okay? Over x plus h minus x is just h, okay? We're taking the limit as h approaches 0. So that's our starting place. That's the definition, fundamental definition of f prime of x. Now we've got to get a little more specific. Now we need to know, okay, well, this isn't just some random f of x. What is our function? Square root of x. Okay, so then if f of x equals the square root of x, what is f of x plus h? Yeah, right? This is just telling me that whatever I'm plugging in, I'm taking the square root of it, right? F of x equals the square root of x. F of 4 would be the square root of 4. F of a would be the square root of a. F of hand is the square root of hand, right? So f of hand is the square root of hand. So this just becomes the limit of the square root of x plus h. That's this guy. Let's color code this. So those are the same, right? Here's our fraction bar. Minus, what's f of x? Square root of x, yeah. Over h as h approaches 0, right? Okay. Well, now we can just flip into calculus mode and just evaluate that limit, right? Okay, what would we do for a limit like that? Which technique are we going to use? Yeah, we got to multiply this, the rationalizing technique. We're going to multiply top and bottom by the conjugate of the top. And of course, it's going to always be this way if I'm taking a derivative. But if I try to evaluate this directly, I get 0 over 0, right? So this is always that kind where we have to do more work. Okay, so let's crank into calculus mode. And so we're just going to multiply this by square root of x plus h plus square root of x, top and bottom. Okay, so what's that going to give me? On the top, what do I get? Limit of what? Good, I get square root of x plus h squared, which undoes the square root, right? So I get x plus h minus x. There you go. Good. And on the bottom, I just get all that junk, right? I get h times the quantity square root of x plus h plus the square root of x as h goes to 0. And what good stuff happens on the top? The x's cancel. Yeah. Okay, so we end up with the limit of h over h times that big factor. And here's where the indeterminacy goes away, right? It always goes away the same way. I have to be able to factor the top and the bottom and cancel the factors that are going to 0, which I can do here. The h's cancel. And now I get a function that I'm able to evaluate directly when I'm taking the limit, right? So what do I end up getting for my answer then? We get, if I let h go to 0, well, let's rewrite this, I guess. On the top, I've just got a 1. On the bottom, I've just got the square root of x plus h plus the square root of x. As h goes to 0, what's that give me? 1 on the top, I'm going to get, that's going to 0, so I get the square root of x plus the square root of x, which is just 2 square roots of x, right? So there's my answer. Okay, that's, I know that you're still in kind of algebra / calculus mode here. And so, that hasn't yet probably struck you what an amazing thing we just did. But now we're done with, we can flip back into kind of just like big picture mode. Look what we just did. We just found a function that gives us the slope of the tangent line to our original function as a function of x. That's huge. We could pick any value of x we want to, and the derivative is going to tell us what the slope of the tangent line is at that value of x. That's absolutely amazing, right? So we started with this, f of x equals the square root of x, and we found that its derivative is equal to 1 over 2 times the square root of x. So let's say we want to know what's the slope of our function at x equals 4. Well, we know it's just 1/4, right? If I want to know what the slope of the function is at x equals 16, it's 1/8. Okay, that's amazing, right? We've got this function that predicts the slope of the original function for any value of x. Now, what value do we want? We want 1. Right, okay, so now we can say, go back up here and say f prime of 1 equals 1/2. Equals the slope of the tangent line. So we had this point of tangency at 1, 1. We know the slope is 1/2. We just throw this into point slope and we're done, right? Remember point slope, y minus 1 equals m times the quantity x minus x1, right? There's point slope. I'm just plugging in the blue coordinates, and I'm plugging in, one more time, I'm plugging in the blue coordinates and the red slope, and that's that. On the AP test, you don't even have to simplify that. You can just leave it in point slope form. That's fine. So we get y minus 1 equals 1/2 times the quantity x minus 1. On the assignments, you got to simplify that, but big deal. You just distribute the slope and add 1 to both sides, and you put it into slope-intercept form. Okay? Yes?
So I'm just confused about when we solved the limit, we did like a two-sided limit. Wouldn't they both be different slopes if you're technically getting?
We don't need one-sided limits here. There's no, right? We are able to resolve it with a two-sided limit. Why do we need one-sided limits? We need one-sided limits at the edges of closed intervals, and we need them for piecewise functions, or we need them if we want to know if functions at vertical asymptote, the behavior at vertical asymptotes. Is a function, as it approaches the vertical asymptote from the left, is it going up to positive infinity or down to negative infinity? Same thing from the right, okay? That's really the purpose of those. But we don't need them here. We're just evaluating this limit, which we're able to do. It's no problem, right? Okay, yep.
So what's the function that we got?
So let's look at a picture. So this is the slope of the tangent to the curve when x is equal to 1. Okay, let's see what we just did. Let's look at a graph. There's our function, right? We're trying to find the tangent to the curve at x equals 1. Okay, well, here is the equation of the line that we just found, right there. That's what we found. What's this thing? Oh, never mind. Okay. Make sense? Okay. You picture that of our handiwork. Okay, so one more thing here, though. We could have, let's go back up to, here. So I want to just, on the last example, we found the derivative function and evaluated it at 1. That's the way I would do this problem. I would find f prime of x and then plug in 1 to find the slope of the tangent line. It's nice to have the derivative function because it's totally general. We can plug in any value of x we want. For sure, if we were going to be plugging in multiple values of x, we would definitely want to do it this way. There is another option, and I'm not suggesting this is a better way to do it, but it's going to help you be able to answer some questions on the assignment, which are based on some AP questions. Okay, so could we have done this by just directly finding the derivative at x equals 1? Right? Could we have just done this? F prime of 1 equals something. Yeah, we could. We could use the same definition of a derivative, but instead of starting at x, we're just going to start at 1, right? So we could write this as the limit of f of 1 plus h minus f of 1 over h as h approaches 0. What's that saying right there? Wouldn't you agree that that is saying f prime of 1, right? That's just f prime of x if we're substituting 1s for the x's, right? Isn't that the definition of evaluating a function, is you're going to plug in a value for x, for all the x's? Okay, so if this is f prime of x right here, then this is the most basic definition of f prime of 1, isn't it? Right? And then we could have done the same math, but we just would have gone to a specific answer instead of a general derivative function. What would that look like? Let's just do this really quick. So that's going to give us the limit of f of 1 plus h would just be the square root of 1 plus h minus the square root of 1 over h as h approaches 0. We could rewrite that square root of 1. Let's just rewrite that as a 1. And why didn't I leave myself more room? Because I'm not very smart. Let's do that. Right, and then all I would do is the same steps I did before. And this is, it's going to seem like I don't want to waste a lot of time on this, but I just want to show you how this works. I would just multiply top and bottom by square root of 1 plus h plus 1, which is going to give me, you tell me, what's the limit going to be on top? Minus 1 over h times square root of 1 plus h plus 1. Well, we could just combine some steps here. Those guys are going to cancel, right? Horizontally. So I just get an h on top, which I could cancel vertically and take my limit, right? And then I just end up with the answer 1 on the top over the square root of 1 plus 1. That's just 2. Okay? You see how those parallel each other, but you see the difference, the subtle difference there, what we did. Okay. Okay, so let's try this a little bit then. See if you could tell me for the following limit. These are just questions that are, like you could see this on an AP test. These are really easy questions, but you just got to understand what they're asking. The following limit represents the slope of a curve y equals f of x at the point a f of a. So there's two parts to this. You got to determine what is the function and what is the value a. So what the point of tangency is going to be at what x value. It's almost easier to start with what is a. This is the derivative, right? So this has got to be equal to this stuff, right? Okay, we're plugging in a specific value for x here, which is 2, isn't it? Everybody see that? How do I find that easily? Well, 2 plus h is equal to x plus h, right? Or a plus h. So the value of x we're plugging in must be 2. Right? So there's one thing we see. A equals 2. Well, what's the function here? Yes? No, just 2, because we want to know what is the value that we have substituted for x. Okay, it is 2. What is the function? Square root of x. How do you know? Well, because that's f of x with x equaling 2, right? That's f of x plus h when x is equal to 2, okay? So I don't know any other way to teach that or see that other than just doing some problems and just thinking about it until it makes sense. It's just one of those things where you just got to just see those connections and just practice it a little bit. Do 3 or 4 problems and it's easy. Okay, try one more. Everybody try that one on your own real quick. See if you can figure out what is the function and what is the value of a. What do you think? Tori, take your pick. You want to tell me the value of a or tell me what the function is? Or both? You can be greedy and do both if you want to. A is 3. Yeah. Okay, everybody agree with that? A is 3. Good. Tori's such a nice person. She didn't want to be greedy. She wants to let somebody else have some fun too. Jonathan, what's the function? I'll tell you where to look. You look right there.
Is it x to the power of 4?
Very close. What are you missing? 2. Yeah. It's 2 x to the 4th. How do we know that? Because what's inside the function here is x plus h, or a plus h in this case, right? So if this is if this part right here is f of 3 plus h, then f of x must just be 2x to the 4th, right? Okay. All right, so what here? 55. Okay, so maybe look at 1 or 2 graphs here. So just a review of the stuff we talked about yesterday, right? If position is s, then average velocity is delta x over delta t. Instantaneous velocity is just the derivative of the position function. How about that, right? And instantaneous acceleration is the derivative of the velocity function. Okay, now this looks a little weird, and we'll talk more about this later, but this is what we call a second derivative. If velocity is the derivative of position and acceleration is the derivative of velocity, then we'd say acceleration is the derivative of position, which we call a second derivative. Okay? All right, so if that's the case, we should be able to have some fun here. I've been waiting to do this one. I made these yesterday. These are pretty cool. Man, I'm really a nerd, aren't I? Okay, so this is a position function. Okay? This is position as a function of time. So time is on the horizontal axis, position is on the vertical axis. Okay, if I start at, let's say this is position 0, what would that story look like if you were to video me doing that? What would I do? No. This is, I'm motion along a line. Make it real simple. Okay, I'm moving to the right. Good. Okay, I move to the right, and what's my, just estimate, what's my maximum for position? Like, what's the furthest I get away from my starting place? 2 point something, right? So I'm going out there like 2 point some meters, and then what am I doing? I'm going back, right? That's the, okay, we could even be more specific about that, though. If we just could tell something about velocity, I could make that story a little more interesting. Right now, all the story is I walk 2.5, I guess that is half of it, 2.5 meters forward, and I walk 2.5 meters backwards, right? What if we could graph the velocity function? Okay, well, let's try that. We can take advantage of the relationship we've talked about. The velocity is the derivative of position, right? So it's the job of velocity to tell what the slope of the position function is. Okay, does that make sense? So listen to this statement very carefully. The value of velocity is equal to the slope of position, right? For any value of x, the velocity at that value of t in this case is equal to the slope of the original function at that value of t. So I want to plot the velocity function based on that graph of the position function. Can you tell me? It's hard to know exact values because it's hard for us to see slopes, but is there any exact value you can tell me? Is there a place on that red curve where you can tell me unequivocally the slope is this? 0. Where is it 0? At the top. So right at 5 seconds. Everybody agree? If I draw a little tangent to the graph there, that's helpful to do. If I draw a little tangent to, oh boy, let's see, I got to do. Take a picture of this thing for now. Ooh, that's big. Okay, so there's my position function. Okay, I know right here at this point, there's the tangent to the curve. That has a slope of 0, doesn't it? So that means that the velocity function must have a value of 0. Okay? What can you tell me about the tangents to the left of that? If I draw a bunch of little tangents, there's a tangent, there's a tangent, there's a tangent, there's a tangent. What are they doing? They start off positive. And what can you tell me about the values of those? They're all positive. Where's the biggest slope going to be? At 0, and they're gradually getting less and less steep. So they're moving towards 0, aren't they? So wouldn't I expect to see something, and that one looks like it's about 1. I don't know, something like that. I mean, we don't have to get the values exactly right. But that one has a slope of about, we'll just say it's 1 or 1 point something. This is 0. So we'll just assume that that's changing regularly, okay? So there's a slope of the velocity function to that point. Now what happens on the other side? What's happening to those slopes? They're getting more negative, and they're edging towards a slope of something like, if I took that tangent right there and extrapolated it, it's probably just a little bit less than -1. So maybe we're doing something like that. That's my velocity function. Everybody see that? Okay, let's see what it actually is. Let's look back at Desmos, and if I turn this one on, oh man, don't you just wish this class was about 4 hours long instead? If I turn on the velocity function, there it is. Okay, that's what we graphed. Okay. Can anybody tell me real quick what the acceleration function is going to be? What's the slope of velocity? It's going to be something like, well, it's going to be constant and negative, isn't it? Right. So wouldn't the acceleration graph just look like that? It's constant and negative. Ooh. Okay, we'll come back and finish this story. It's an interesting story. We'll talk more about it tomorrow.